we're talking about crystallographic root systems. And last time I proved for you this nice result that tells you how to go from the Cartan matrix of a crystallographic root system to the Coxeter matrix of the associated Coxeter group. Okay? So remember that, first of all, remember that these things are indexed by simple roots. Okay? And Aij is the inner product of alpha I and alpha j check, and Mij is the order of the group element Si, Sj. Okay. And so this is how it goes. So if you know the Cartan matrix, this is how you read off the Coxeter group. Okay. But one thing that we have not discussed, and I haven't shown to you, is that, I mean, I did show to you that if Aij, Aj takes these values, then Mij takes these values. I proved to you that this number has to be well, we know it's an integer by definition of crystallographic. Crystallographic means that the Aij's are integers. And I proved to you that this product cannot be negative, because Aij, we showed, was always non-negative. So non-negative times non-negative is non-positive. What I have not shown to you is that all of these numbers actually appear in crystallographic root systems. In other words, that Aij, Aji really can take the value of any non-negative integer. And so what I'm going to do first today is to actually show you some root systems that realize all of these numbers. Okay. So now I'm going to show that all of these are possible. All of these values of Aij, Aji are possible. And not only are they possible in theory, they're actually realized in rank 2. Okay. That means that they're realized in any other rank. So let's go ahead and do this. So first let me show to you that A12, A21 could be 0. Okay. Well, that's not surprising. We know that. That just means that alpha 1 and alpha 2 need to be perpendicular to each other. Okay. And here's an example of that. This is the root system where this is alpha 1 and this is alpha 2. Okay. And the Coxeter matrix of this thing is 2, 2, 0, 0. Okay. So that's easy. What about A12, A21 equal to 1? Sorry, this is the Cartan matrix, not the Coxeter matrix. Here the Cartan matrix should look like this, 2, 2. We need two negative integers that multiply to -1, so this is the only option. Okay. And so what we're going to do is the following. Now let me remind you of something that is going to be useful in constructing these things, which is that we showed this, that Aij divided by Aji is equal to alpha I comma alpha I divided by alpha j comma alpha j. And the reason this is going to be useful is that it'll help me set the correct length for the roots. Okay? This tells me that I don't have complete freedom over this. For example, in this case, Aij and Aji are both equal to 1, and that means that alpha I and alpha j should have the same length. Okay? And so let me see if I can pull this off with length equal to 1. Hopefully I can. Okay. then what do I need? Well, basically I need alpha 1, alpha 2 check to be equal to -1. Okay? And of course, by this relation, if I manage that, then I'm going to get that alpha 1 check comma alpha 2 is also equal to 1. Okay? So I just need to make this happen. Okay? Now, what is alpha 2 check in this case? Well, alpha 2 check is 2 alpha 2 divided by norm of alpha 2, which is 1. So it's 2 alpha 2. Okay? So that means that what I need is that alpha 1 comma alpha 2 should be -1/2. Okay? Now, I'm trying to do this in Euclidean space. Maybe you noticed already. So I'm trying to do this in Euclidean space. And if I know the length of alpha 1 and alpha 2, and I know the dot product, then basically this just tells me what angle I should have. I should have the angle between them whose cosine is -1/2, right? And what is that? That is 120 degrees, 2 pi over 3. Okay, so this is alpha 1, this is alpha 2, and then it's not surprising, this is a root system that we know. Okay? If you reflect around, you find this root system. Okay? But it's good to do this, not just show you this, so that you see that this was kind of forced upon us. If you want to do this Euclideanly, and you want length equal to 1, then this is the root system that you get. Okay. Let's do the next one. So 12821 is equal to 2. Let's try to do it in R2 also. And again, well, now it's a little bit different, right? Because I need two numbers here that multiply to 2. And so I have two options, -1, -2. Or -2, -1. Now, it doesn't really matter too much because if I switch them, then all I'm doing is changing the roles of alpha 1 and alpha 2. Okay? So let's try to do it like this. Okay? Now, what this tells me is that I cannot make both of these of unit length, right? Because alpha 1 comma alpha 1 divided by alpha 2 comma alpha 2 is going to have to be 1/2. So let's try to do this with alpha 1 having length 1 and alpha 2 having length, should have length root 2, which means that the dot product with itself is 2. Okay? That way this divided by this is equal to this divided by this, as it should be. Okay? So here what I need is that alpha 1 comma alpha 2 check is -1, right? Now what's alpha 2 check? Well, alpha 2 check in this case is 2 alpha 2 divided by 2. So this is alpha 2. So what I need is alpha 1 comma alpha 2 should be -1. Okay? So I want to construct two vectors, one of length 1, one of length root 2. Their dot product should be -1. And that means that the cosine of the angle should be -1 over root 2. Or maybe we prefer writing it like this, minus root 2 divided by 2. Okay. And again, we know what angle that is. So basically, I make alpha 1 of length 1. I make alpha 2 of length root 2. And the angle should be 135 degrees. So it should be like this. And it should be length root 2. And the root system that you get looks like this. So this is alpha 1. This is alpha 2. Okay. And so again, this thing just comes out naturally. Okay. Now I should tell you what would have happened if we switch the -1 and the -2 here. Well, basically what we're going to get is a very similar thing, except that it's going to look like this. Now this, instead of a 2, it's going to be a a 1/2. So what we're going to get is that instead of alpha 2 being the long root, it's going to be the short root, and it's going to land right there. And so these are two realizations of, these are two crystallographic root systems that give me this number. Okay. So now we're going to do A138, sorry. Well, A12, A21 is equal to 3. Okay. So again, now the matrix is going to look like 2, 2. I need two numbers that multiply to give me 3. So they have to be -1 and -3. And so if I assume that alpha 1 comma alpha 1 is 1, then I'm going to be forced to choose alpha 2 comma alpha 2 to be square root of 3. Okay. I need alpha 1, alpha 2 check to be -1. Sorry, 3. So the length is root 3. The dot product is 3. Thank you. I need this, and if you compute what this is, we find that alpha 1 comma alpha 2 should be -3/2. And if you compute the cosine, you find that it has to be minus square root of 3 over 2. Okay? And again, we know what angle has that cosine. And so you have to choose something of length 1 here, something of length root 3 at the correct angle. And if you draw the picture, you find that this is what you get. Okay? So I really wanted to draw this ahead of time so that it actually looks the way it looks. It's not the easiest picture to draw. Okay? So this is a realization of this root system. This is a root system in R2. It's crystallographic. Okay? Just to make sure you see the geometry of this, basically what happens is that there's kind of two equilateral triangles hugging each other here. So here's one of them, and here's the other one. Okay. And this is what I wanted to draw ahead of time, and I wouldn't be able to if I do it live. Even then, well, it's not bad. So that's why it's a nice root system. It's a nice picture. Okay.
So if you switch from the -1 and the -3, like over here, you kind of got something. That's not the same. Those aren't the same root systems, right?
So here, right? So I could change the -1 and the -3, and what that's going to do is that now the purple, instead of being the long roots, they're going to be the short roots. And if you want to know what they look like, you have to go like this. Actually, maybe I can do this live, because all you have to do is this, and then you know what the purple ones are. It's like this, like this, 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 like this, and
there's like a rotation and contraction of that lattice.
yeah. But I mean, these things, okay, I call them different, but they're not really that different. They're just the same thing, except, you know, maybe relay will rotate its scale, but they're basically the same picture. Okay. How about by the way, I should just tell you what these things are called, because these root systems have names. So this one, if you think about it, this is just kind of the product of this root system times this root system. So two things that are going on in independent planes. Okay. So that's why this root system is called A1 cross A1, because A1 is the root system correspond to a single root. This one is the root system A2, and we know that it corresponds to the group S3. This guy is called B2, and this guy is called C2. And you'll see, I'll explain to you in a second why these have different names, even though these have the same name. So this one is called G2. So you can imagine the subscript refers to the rank. So all of these things have rank 2, which is why they have sub 2s on them. Except for this one, it's a product, but so you add up the ranks. So we'll see why B and C deserve different names, but G does not deserve a different name from the other version of it. But I'm not done because I have to do the case, this case. Okay? So now my matrix looks like this, where A and B are integers whose product is greater than or equal to 4. Okay? So I'm supposed to choose these lengths so that this divided by this is A over B, and so it's natural to try to make this equal to A and try to make this equal to B. Okay? And if not, we just rescale. So what do we need then? We need that alpha 1 comma alpha 2 check is equal to minus A. And if you compute what this means for alpha 1 comma alpha 2, you find that what you need is that this is minus AB over 2. Okay? And so the question is, can I find 3 vectors like this? Okay. Now, we should have done this ahead of time, but let's do the cosine. So what cosine do you get? Well, this is supposed to be square root of this times square root of this times cosine of the angle. Okay. So what I get is minus AB divided by 2 square root of A square root of B. And so what I get is minus square root of AB over 2. So I need an angle whose cosine is minus square root of AB over 2. Okay? Good luck finding that. Good luck finding that because AB is greater than or equal to 4. Okay? And so this number is, if AB is bigger than 4, then this number is smaller than negative 1. So there's no such angle, theta. One thing. Second thing, if AB is equal to 4, then the cosine would be negative 1, which means that these things are not linearly independent. Okay. So then what? Am I done? Does that mean that I can't construct this thing? Well, I can't construct the thing in R2, which is where the usual dot product makes sense, where we really can talk about angles and things. Okay. This is not going to work in R2. This is the proof. Right? So that means that I'm going to have to build myself one of these unusual inner products. Okay. But so I can do this. I mean, the point is I have to choose an inner product on R2. Okay. How do I define an inner product? Well, by defining on a basis what are the products of the things in the basis. Alpha 1 and alpha 2 are a basis, and so if I just define, so let me just say, so now let alpha 1 and alpha 2 be a basis for R2, and let me just define an inner product by just forcing these things to be true. And nothing can stop me from doing this because alpha 1 and alpha 2 are independent. They are bases, so I can freely choose these numbers. Okay? And then I say, okay, well, then just build the root system. How do I build the root system? Well, basically, the simple roots are alpha 1 and alpha 2. Okay? And what are all the roots? Well, all the roots, we know what they have to be, right? They have to be whatever you get when your group acts on the simple roots. What group? The group is the Coxeter group associated to this, and that Coxeter group is generated by the reflections S1 and S2. Do I know what S1 and S2 are? Well, I do because I know the inner product. So S1 of V is just V minus 2 V alpha 1 check alpha 1, and S2V is the same thing with alpha 2. Okay? And so then I just define it in this way. These are the simple roots. The roots are obtained from the simple roots by applying these two operations as many times as I want. And, well, then I have to check some things because I can't just say this is a root system. I have to prove that this is a root system, and so this takes a check. It's a good exercise that I'll leave for you. Check this is a root system. Now, why is this a reasonable exercise? Because this group is very simple. Okay? It has two generators, and we know what is the order of S1, S2. Right? All we have to do is look at that table. We know that if Aij, Hij is bigger than or equal to 4, then Mij is going to be infinite. Okay? So we know what this group is. This group is just going to be isomorphic to the infinite dihedral group. Okay? And that means that I understand exactly what the elements are. It's not just like you're reflecting in some random way. The elements of this group are S1, S1, S2, S1, S2, S1, etc. Okay? And so what you have to do is then see how that acts on this, which is then, you have to do infinitely many things, but you have to check S1 alpha 1, S1 S2 alpha 1, S1 S2 S1 alpha 1, and then at least this is a manageable computation. And so the exercise for you is to do it. And I should tell you that, how do you check that something is a root system? Well, you check these 5 properties of root systems. And if you go down the list, you're going to see that almost everything is trivial. The one property that is not trivial is that if you have some random root in phi, then it's either a positive combination of delta or a negative combination of delta. That's the only tricky thing to check. And so then you basically have to just compute. You have to see what these things look like and show that they're positive or negative combinations of alpha 1 and alpha 2. Okay? But so when you do this computation, you find that this is always possible, and that completes my claim that all of these values of Aij, Aji are possible, and that also means that all of these orders Mij are possible. Okay. Let's introduce some notation now. do it over here. Something called the Dynkin diagram. Of a root system. Crystallographic root system. So the Dynkin diagram is going to look like this. The vertices are going to be the simple roots. We call them alpha 1 up to alpha n. Okay? And the edges are going to look like this. So basically I have to tell you for each pair of vertices. So the Dynkin diagram is a graph with labels on it. So what's the graph? The vertices are the simple roots, and the edges, I have to basically tell you for each alpha I and alpha j, do I put an edge there or not? Okay. Well, there are several cases. What I do is the following. What I do, it depends on this table. So if aij, aj is 0, then I don't put an edge. Okay. If, well, let me put it this way. So we know that if the product is 0, then both of them are 0, because we said that the zeros are located symmetrically. So if they're both 0, it looks like this. Now, if the product is 1, that means that they're both negative 1. Okay. And in that case, I join them. Now, the next case is that it's 2. And so that means that one of them is -2, and the other one is -1. Okay. And so in that case, what I do is that I put, first of all, I put a double edge like this, okay, which corresponds to this 2. And second of all, I put an arrow that indicates, because I know that these two things have different length, right? I know that the length of I divided by the length of j is basically 2. It's the square root of 2. And that means that this guy is longer than this by a factor of square root of 2. And so I put an arrow to indicate that out of these two roots, this is the long one, this is the short one. Okay. Now you can imagine what I do in the next case is the same thing. Now I put a triple edge. Okay. And again, the length of alpha I divided by the length of alpha j is square root of 3. And so I indicate that with an arrow like this. Okay. And the strange thing about Dynkin diagrams is that people haven't made up their minds as to what to do in this case. And people use different notations. Now, you can imagine the reason is that these are the ones that people care about the most. But here, if you have a and b with a b greater than or equal to 4, then what you'll see sometimes is this. Put an edge like this, and then just tell what the numbers are. A and B. Okay. So I don't know. If this is -3 and this is -7, then you just put a 3 here and a 7 here. That's the Dynkin diagram of a root system. Now, of course, by this result over here, I know that the Dynkin diagram of the root system is closely related to the Coxeter diagram of the related Coxeter group, right? Because the Coxeter diagram also has as vertices, well, the generators, which I also call delta, okay? And what edges do I have? Well, if aij equals aji equals 0, then I know that mij is equal to 2. And if you remember in the Coxeter diagram, the way that I represented that is by saying that there was no edge between Si and Sj. In this case, Mij is 3. And so that we represented with a single edge. If Mij, in this case, Mij is 4, which we represented like this. In this case, Mij is 6, which we represent like this. And in this case, it's infinite. Okay. And so that means that if you know the Dynkin diagram of the root system, you know the Coxeter diagram of the group. Okay. And you can almost go backwards. I mean, you can go backwards in some cases. So if you see an edge like this, you see what's over there. If you see an edge like this, you know what's over there. Here, you almost know, except that you don't know the arrow. Okay. And here, the same thing, you don't know the arrow. And here, there's much more. If you see an edge like this, then A and B could be any numbers that multiply to something bigger than 4. So you can partially return, but not always. So examples of Dynkin diagrams. Well, I just did a bunch of examples. So for example, A1 cross A1 looks like this. We talked about these examples, right? A2 looks like this. B2 was the case when we had a 2 there, and it looks like this. And in C2, you just reverse the arrow. Okay. Now G2 was the case Aij, Aji equal to 3, and so we have a triple arrow, and it looks like this. And you might be tempted to reverse the arrow. And again, I'll tell you in a second why. When we reverse the arrow, we still call that G2. And I guess I didn't tell you the name of this one, but we know that we have a root system for any A and B, for AB greater than or equal to 4. And this is called I2 of A, comma, B. Okay? Let me give you some more examples. We talked about the root system of the symmetric group, which has n minus 1 edges, sorry, n minus 1 vertices. The roots we said are E1 minus E2. I guess we said it the other way around. E2 minus E1, E3 minus E2, dot, 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 until En minus En minus 1, the last one. So we showed that this was a crystallographic root system. Okay, it's the crystallographic root system of the symmetric group Sn. And now you see why the subgroup that I always put on it is n minus 1 and not n. The reason is just that it has n minus 1 vertices, so it's a rank n minus 1 thing. Okay. Now, if you remember, we also did this for the hyperoctahedral group. Okay. And we said that in that case, the roots look like this. You basically added an E1 at the beginning. And remember we said that when you think of EJ minus 1, you're kind of thinking of switching adjacent cards in the combinatorial picture. And here we talked about how these operations are like changing adjacent cards. And E1 is like the operation of taking the top card and flipping it. Okay? So you see this is a crystallographic root system also. But you see now this label changes because this has length 1. This has length root 2. Okay? This is a double edge. And it goes from the big root to the small root. So that's the picture for Bn. And you can imagine that the picture for Cn is the same thing. Except that it goes the other way. Because in this case, this root is big. 2e1. It has length 4. Sorry, it has length 2. It has norm 4. And that's why we call B2 and C2 of different names. Really, B2 and C2 are isomorphic. They're isomorphic as root systems. But they're parts of a bigger family. And these guys are not isomorphic for n bigger than or equal to 3. They really are different. Okay. Now, the thing about G2, which makes it different from B2 and C2, is that G2 does not have an analog in n dimensions. Okay. And that's why we don't give it another name when you flip it, because, I mean, this is the reason that we give Bn and Cn different names. But G2 is kind of an anomaly that only lives in 2 dimensions. There's no analog here. No analog of this. And there's no analog of this either. So these are some Dynkin diagrams. Okay. Okay. Well, let me say no nice analog, and we'll see what nice means. But these are nice groups that correspond to this. Nice, finite, etc. So what happens now? We were talking about Cartan matrices, right? So remember that what we're trying to do is to classify crystallographic root systems. We said that a crystallographic root system was basically the same thing as a Cartan matrix that was integer. Okay? So we're classifying Cartan matrices. Now, if you look at this, if I give you the Dynkin diagram, that means that you already know the Cartan matrix, right? Because if you see this, you know that the Cartan numbers are 0. If you see this, you know the Cartan numbers are -1, etc. Okay? So classifying integer Cartan matrices basically is the same thing as classifying what are the Dynkin diagrams of crystallographic root systems. And we're finally in a position to answer this question. So here's the theorem. If I give you a diagram like this, does it come from a crystallographic root system? Or equivalently, if I give you an integer square matrix, is it a Cartan matrix? An integer square matrix is a Cartan matrix of a crystallographic root system if and only if the following conditions hold. So we talked about some very simple conditions. For example, we saw that in the diagonal, you better see 2, all 2s. We talked about how off the diagonal, the numbers better be non-positive. we talked about how the zeros are distributed symmetrically. I told you this was not enough. We're missing just one condition. And this is the last condition. It's the following. Along every circuit, let's call it I1 up to IK of the Dynkin diagram, we have to have a certain relation. Now, here we see no examples of this because none of these Dynkin diagrams have circuits. Okay? But if you were to see a circuit like this, up to IK, then there's a very simple relation that has to hold, and it's the following. AI1 I2 divided by AI2 I1 multiplied by AI2 I3 divided by AI3 I2 multiplied by etc. up until AIN I1 divided by AI1 IN should be equal to 1. Okay. K. Okay. So, what's an example of a good circuit and what's an example of a bad circuit? I don't know. Let me just do something. So this. Does this look good or bad to you? I don't know. You have to check. So how do you check something like this? Okay, well, what does this mean? This means, I mean, these edges don't have the numbers written on them, but we might as well. So when you see something like this, you know that the AIJs are both -1s. And this we go from big to small. So 2, 1, 3, 1, 2, 1. Let's see if I actually managed to do this correctly. So what do you do? 1 divided by 1 times 2 divided by 1 times 1 divided by 3 times 3 divided by 4 times 1 divided by 1 times 2 divided by 1 times 1 divided by 1. And beautiful, 1. Yeah, you multiply these numbers, you get 1. So this is a good circuit. Good circuit. This circuit might occur in the Dynkin diagram. But if I make this a triple edge and put a 3 here, then all of a sudden this product is not 1, and that makes it a bad circuit. And that means that you're never going to see this. Okay. This is my theorem. Well, not my theorem. This is the theorem describing what Cartan matrices look like exactly. Okay. So let me say a couple of words about the proof. So first of all, what is this strange condition saying? I mean, we understand what this means, and what this means. We already proved these things. Okay. What is this last condition saying? Well, if you think about it, this last condition is actually quite simple to see why it's true. The reason is that AI1, AI2 divided by AI2, I1, we know that this is the inner product of alpha I1 with itself divided by the product of alpha I2 with itself. Okay? And so this is a telescoping product. Do you guys know that word, telescoping product? So this is the length of alpha I1 divided by the length of alpha I2, the length of alpha I2 divided by the length of alpha I3, alpha I3 divided by alpha I4, and so each guy cancels each numerator of these cancels the previous denominator, and it cycles around, and so you get the power of this one. So people talk about these as being telescoping. Each thing cancels something in the next one. So this proves necessity. Okay. And the question now is sufficiency. So if I give you a Cartan matrix that has these properties, how are you going to construct a root system for which this is the Cartan matrix? Okay. Now, one way of constructing a root system is from a Coxeter group, right? And so the question is, can I build first the Coxeter group and then the root system? Okay. But you see, the thing is that if I know the Dynkin diagram, then I know the Coxeter diagram. And if I know the Coxeter diagram, I know the Coxeter group. Okay. So take the Dynkin diagram. Okay. Now, from that simple combinatorial rule, I can generate the Coxeter diagram. And given a Coxeter diagram, I know how to generate a Coxeter group. Given a Coxeter group, I know how to generate a root system. You see how much we've learned in this class? It's amazing. This is what we call the geometric representation of the Coxeter group. We can do this for any Coxeter group, any Coxeter diagram. And now the tricky thing is, okay, well, I have a root system. Does it have these properties? If you look at what you did, you find that this is a root system having this Cartan matrix. The only thing that you don't know yet is whether it's crystallographic or not. Okay. Crystallographic. And actually, you're going to find that it's not crystallographic. And let me explain to you why it's not crystallographic. Because in this construction, from a Coxeter group to a root system, the way that we did this, the roots always had length 1. Okay? And we know that for something like this, you're not going to be able to pull it off having all lengths equal to 1. Okay? And so the last thing you have to do is just rescale the roots to give them the correct lengths so that they become crystallographic. Okay. So this is not crystallographic, but then you rescale it nicely. Rescale roots to make them crystallographic. And how do you rescale them? You see, actually, it's kind of forced upon you. And that's good, because you don't want to have to make any decisions. You want the picture to tell you what to do. You don't want to put your hands in there and ruin anything, right? So how are you going to rescale? Well, basically, you're supposed to assign lengths. Okay? And so you say, okay, well, maybe this thing really did have length 1. Then what length should this one have? Well, it has to have length 1 also because these are both 1s. Okay. Now, what length does this thing have to have? Well, we know that the ratio between this length and this length should be the square root of this. And this is the big one and this is the small one. Okay, so this is 1 over square root of 2 in length. Let me switch this again to my good example. So originally this was a 2. So I keep going. Here, the ratio should be a third. Now this is the short one. Sorry, square root of 3 should be the ratio. This is the short one, this is the big one. So that means that this thing should have length square root of 3 over square root of 2. Okay. Now here, the ratio should be 2 over square root of 3. So that makes this guy have length square root of 2. Now these are 1s, so this thing has to have length square root of 2. This is ratio square root of 2, and this is the big one, so this has to have length 1. And now we can breathe, because we didn't want this to be a different number. We wanted this to prescribe the same length when you go around the circle. Okay? Why did we get the same length when we went around the cycle? Precisely because of this condition. And so you just kind of do this for the whole graph, and you're not going to have any mistakes. And the reason you don't have any mistakes is because this saves you. Okay. So that's a sketch of the proof. That's really all the interesting parts, and then there's little details to check here and there, but this is really the essence of the proof. Okay. It's a nice proof. I like that. Okay. See you guys next time.